So SuperPave, we talked about SuperPave before, and we mentioned that SuperPave is basically referring to a mixed design process for designing the hot mix asphalt pavements. And this is not the structural design, this is the mix design. So we are designing what type of binder we're using, we're designing what type of aggregate, and how much from coarse, fine, and different types of binder we're using in the mix. So SuperPave mix design. We will start with the process that this process was adopted to simulate the actual traffic resistance or traffic performance of the pavements. And also there is an improved version of binder classification, because the previous binder classification was only based on penetration rate, and that was not very detailed and effective in terms of showing the fatigue parameters of the binder. And so the researchers have started looking into and developing a new classification, binder classification based on performance grading. That's why they call it the PG binder classification system. And then there is a compaction process required for the SuperPave mix design, which is more representing the actual traffic conditions. Now, before the SuperPave mix design, there was other test methods to design the mix. The first one was the Marshall mix design, and also the Veeam mix design method. And again, these are the methods to design the type of aggregate, the gradation of aggregates, and what type of binder, and also what binder content you'll be using for the mix, the hot mix asphalt mixture. The Marshall mix design and basically the previous ones are based on stability or strengths, and also the flow of the target mix design. And also there was a target void content or air content in the mix that will give us the final mix design will actually give us the optimum binder condition or optimum binder contents, right? So for example, if you have different binders starting from 3.5% all the way to 5.5%, and you perform a bunch of tests in the lab on different samples, and you measure their stability, flow, void content, and other parameters, and then from the Marshall test method, you will be able to find the optimum binder content. For example, let's say the optimum will be around 4.5%, right? But this is again based on previous binder classification system. Which was based on penetration rate only. Right? Now, although this was a very simple and straightforward method, it was not providing enough details um, for the mix design and also the performance of the mix. That's why the SuperPave mix design was proposed to as a more comprehensive method. All right, so one of the important aspects of the SuperPave mix design is the compaction process. So let's talk about the compaction process. And this is important both in the lab and also in the field. When you are mixing the lab samples, it is important to what method of compaction you're using, what compaction energy you're using to compact the lab samples, and that will be translated to the field operations, what type of roller, how many passes of roller you need in the field to compact the hot mix asphalt to reach the target density in the field. Right now, the compaction process in the lab, the goals of compaction process is to simulate the field classification. So to simulate the field conditions, both in terms of traffic and also climate data. So it is important to consider the traffic parameters and also consider what type of climate conditions we are designing the pavement for. And also we want to accommodate for large, so accommodate large aggregate size. We also want to know what is the compactability of materials. So to estimate the compactability, so estimate the compactability. And also to perform the QC, the quality control process. Quality control or QC process. Right? So these are the goals of why we are doing the compaction process in the lab and how we correlate it to the field data. To do that, we are using a method that is called SuperPave Gyratory Compactor, so or SGC, SuperPave Gyratory Compactor or SGC. So the basics of this device is that it is a chamber for a cylinder that rotates at a specific speed and also at a specific angle and it's basically applying an actual pressure during the rotation to, this is the rotation angle, and it's applying a pressure during the rotation process to basically show or simulate the field process when the hot mix asphalt is being compacted in the field. The diameter of the samples is 150 millimeters. That's the standard diameter. And for different different types of testing, we can have different sample height based on what type of test we are targeting to do in the lab. Now, this is an automated device that we are just controlling the parameters that we are, for example, the load that we are applying to the sample, the rotation angle, the number of rotations or gyrations, and then the sample, we just pour the loose sample inside the mold into the chamber, and also and then the device will automatically compact and prepare the sample. Now, some standard numbers are the pressure is usually 600 kilopascal, right? The rotation angle is usually 1.25 degrees. And the number of gyrations is 30 gyrations per second. I'm sorry, 30 gyrations per minute. So these are the standard machine setup. And there are many different manufacturers that produce and develop the gyration system. And I'm going to post a couple of pictures here in the notes, and you're going to see it in the notes for some standard gyration machines, so that you see how they look like in the lab. Okay, so what you get from the gyration machine is you basically can draw a graph that on the x-axis you have the log. In the log, it's actually a log scale x-axis, and you have the log of the number of gyrations. So it's, let's say, 10, 100, and 1,000. And then on the y-axis, you have GMM. That's one of the density measurements that we do for HMA, hot mix asphalt. I'm going to go over different types of GMM or density measurements for hot mix asphalt. And basically, we expect that the density will be increasing with higher gyrations, with higher number of gyrations, right? Until it reaches a maximum value and it stops increasing. That's we use this for as our compaction curve to know how many gyrations we need to reach before we have a specific number of a specific value for density. Okay, so we usually for the gyratory compaction we evaluating the density of HMA at 2 points. That's the number of at the initial point, the number of gyrations, and also the number of gyrations that we call it N of design, that the design and n is the number of gyrations. This is the number of gyrations. Okay, so that's the number of gyrations. Based on these two number of gyrations, ASHTO, or American Association of State Highway and Transportation Officials, they are providing based on the traffic level. So based on traffic level, the compaction level can be different based on what is the initial number of gyration and what is the design number of gyration. So for example, if the traffic level is less than 0.3, we have 6 for the initial gyration and 50, that's for the design gyration between 0.3 to 3. We have 7 and 75, and we're going to talk about this later on, between 3 and 30. We have 8, and the design number of gyration is 100, and if it's greater than 30, the initial will be 9, and the design is 125. Okay. And so based on these, we can start looking at what are the 4 steps of a SuperPave mix design, right? So 4 steps of the SuperPave mix design. Now, step 1 is, of course, material selection. So we need to know what type of material we're using, what type of aggregates, and what type of binders. So in terms of aggregates and binders, or any type of admixtures that we probably want to add, then we want to design the aggregate structure. So design or aggregate gradation. So designing aggregate gradation. And then designing aggregate, designing binder content. So design binder content from the gyratory test. Right? And then there's one more level here that we want to estimate the moisture susceptibility or moisture sensitivity. And that's measured from a half cylindrical sample, and we measure the tensile strength ratio. So tensile strength ratio, or TSR, is measured for a sample that is been in water at a specific temperature for a set amount of time, compared to a sample that has not been in water and has not been cured in water. That's how we measure the TSR, or the tensile strength ratio. Okay, so let's go step by step for these, and we'll see how each step is working. So the first step is material selection. So step 1, material selection. And we have 2 types of material to select. The first one is binder selection. So binder selection and also aggregate selection, right? Okay, so for binder selection, we need to do or follow the new SuperPave binders specification grading system or performance grading system, PG system, because the type of binder is very important in terms of fatigue performance or rutting or any other pavement related performance. And also the choice of aggregate is very important, and most of the time is usually limited. So usually it's usually limited to local materials. And this is again following PG binder classification systems. All right. And the new binder classification system is based on 2 numbers. So the old one, before we starting the binder classification, the old binder classification system was, for example, again, we mentioned that it's based on the penetration rate. So we drop a standard needle from a standard high on a small binder sample, and from the time from the actual penetration over a specified period of time, we can measure or we can classify that binder. For example, they would classify uh, binders with the range of penetration, like 60-70 or 50-60 and so on. So that's based on range of, this is based on range of penetration rate. Whereas the new binder classification system, so the new binder classification system is using only 2 numbers. And those 2 numbers are the average of the low and high temperature that we want to select. For example, PG 52, 28, or PG 58 and 34. Right? Those are coming from the average pavement minimum and maximum temperature in the area that we are looking at designing the binder classification system. Now we have another specific session for binder classification, and we're going to talk about um, uh, exactly what kind of binder classifications are and what parameters we use for the binder classification. So for now, just know that the first number is the maximum design temperature. And the second number, and a lot of people read this not correctly. The correct way of reading this is PG52 negative 28 or PG58 negative 34. It's not dash because it shows just two numbers. It shows the range of a temperature. So it means that this binder is good for the range of 52 to negative 28 degrees Celsius of design temperature, right? So the second number, the negative 28, is actually the minimum design temperature. So minimum design temperature. And then there is a table, a full table. I'm going to insert the table later on here, and you'll be able to see that. So this is the binder performance grades. And based on the maximum temperature, you'll see different types of binder. And there are a bunch of standard tests for the binders that we will talk about later on when we talk about the PG system. All right. So that's all we need to know for now about the PG system. And we will go back to the actual design process of the SuperBig Mix Design. Okay, so let's that's all we need to know now for the binder selection. And the next step was aggregate selection. So aggregate selection. So for the aggregate selection, we need to look at, of course, the local sources for aggregate. So local aggregate source. And there is a specific limit for, specific limit for aggregate gradation. That we want to be our gradation curve be within those specific limits to be able to design and select for the mix, for the hot mix asphalt mix. There's also another criteria in terms of coarse aggregate angularity. So coarse aggregate angularity. And that will define the number of fractured faces. So you have to follow, you have a number of fractured faces. Based on what is the nominal maximum aggregate size. So I'm going to insert that table as well here to show how that works and what type of criteria we use for aggregate angularity. As well as the coarse aggregate angularity, we need to also care about the fine aggregate angularity. And these are all the tests that you probably remember we've done in the civil engineering materials lab before. So that's how we use, that's one of the applications of the test that we used to do in the lab. So fine aggregate angularity. And then there is another criteria for the number of, or the amount of flat and elongated particles in the mix. Again, we want to limit the amount of flat and elongated particles in the mix to be able to make sure that we have the required performance. And then another test that we need to consider is the sand equivalent test. All right.